So in this video, we'll talk about the geometry of linear combinations. We've been talking about linear combinations before, but we haven't seen many pictures, so we're going to start talking about some pictures. So geometry of linear combinations. Let's just look at a simple example. Let's just look at the system of equations negative 5x1 minus 3x2 equals 4, 2x2 equals 10. Well, it's pretty easy to solve this. So, for instance, the second equation tells you that x2 is 5. And then what do you get? What do you get for x1? Well, let's see. The negative 5x1 minus 3 times 5 equals 4. And add 15 to both sides, so negative 5x1 equals 19. And then x1, you divide by negative 5, you get negative 19 over 5. So the solution is x1 is 19 over 5, x2 is 5. Okay. So now I want to talk about how do you represent this in terms of vectors. So let's review. How can I write this system of equations as a single equation, one equation involving vectors? Okay, let's go over the answer. So I hope you know that this is the same as writing it as, so this is 0x1 plus 2x2 is 10. So I'm thinking of x1 times the vector, so I have this vector here, negative 5, 0, and then I have this negative 3 and 2 multiplied by x2. So it's going to be x1 times negative 5, 0 plus x2 times negative 3, 2 equals 4, 10. So this equation, right, this system of equations can be re-expressed by using one equation, right? There's only one equal sign here, with vectors. Okay, so these two are the same. So it's really important in linear algebra to be able to quickly go back and forth between these two, because it's important to be able to do that in order to understand how systems of linear equations, right, how something like this is related to vectors. Okay. And what's nice about this is that here you actually have a picture. So one picture that you have of this, okay, so let's look at a picture. Let's look at this vector. Okay, let's call this vector v1, and let's call that vector v2, right? And let's call that vector b. I'll usually use b for this kind of output vector. So where's v1 and v2 and b in this coordinate system? Well, negative 5, 0, okay, let's just say it's here. How can I move this up? Okay. Negative 5, 0, that's negative 5 and then up 0. So here's v1. And then negative 3, 2 is maybe here, negative 3 and then up 2, right? Okay, so there's V1, and then that's V2. And where's B? B is 410, so 4 units to the right and then 10 up. Okay, maybe here. Well, I'll use a different color. I'll use green. Maybe I won't use green. I'll just use black. So, oops. So, 410. Like that. So, let's say that's B. Now, how do I interpret the solution that we found, that x1 is negative 19 over 5 and x2 is 5? Well, it's telling me that if I take negative 19 over 5 v1, right, negative 19 over 5 of this vector, and then I add 5 of the second vector, negative 3, 2, I will get 4, 10. And let's see what that looks like in terms of the picture. So if you take this vector v1, right? Oop, wow. If you take this vector v1 and then do negative 19 over 5 of that, so that's like almost negative 4. So the negative is going to move the v1 in the opposite direction, right? So negative 19 over 5 v1 is going to look something like well, that's going to be 19 comma 0. Okay, so that's going to be like this. So this is negative 19 over 5 v1. And then if I do 5 of v2, well, 5 of v2 is going to be like 5 times the length of this, v2. So then if I add it, let's see, that's 5v2. And you see, if I add negative 19/5 v1 plus 5v2, I'm going to get b. So that's how to interpret, you know, this equation in terms of the picture. Now, what would happen if I had a different b? So instead of 410, let's say I changed it to something else. Then would you be able to solve the system? Or you want to think about it? Can you change 410 to? Can you change these numbers to different numbers that will make it not have a solution? Well, the answer is no. No matter what b, no matter what this vector is, this vector, no matter what this vector is, you're always going to be able to write this vector as a linear combination of v1 and v2. And that has to do with the fact, so like let's say that you have, let's say you take a different vector, you know, and make it like there, or something, I don't know, b prime. Well, this one you could probably just take a multiple of v2 and get b prime. Or if you take, you know, something like this, you might, you know, you can take a certain number of v1s and a certain number of v2s and then get this arrow. In fact, if you think about what are all the linear combinations of v1 and v2, so, you know, if you do v1 plus v2, right, you're going to get this vector, I'll do it in green. Like this vector would be v1 plus v2. If I take all the scalar multiples of v1, I'm going to get this line. And what happens if you take all the scalar multiples of v2? well, you're going to get the whole line that goes through v2. And, if you take 2v1 plus v2, you're going to get this vector. Right? And if you take v2 minus v1, so that's negative v1 plus v2, you're probably going to get a vector like this. And if you imagine thinking about all the different combinations for all the real numbers, right? So c1 v1 plus c2 v2, where c1 and c2 are any real numbers, you're actually going to get the whole plane. Like, you're going to get all the vectors in R2. So that tells you that the span, okay, maybe right, the set of all linear combinations is all of R2. And so I'll just write that down. So the span of v1 and v2 is R2. So in R2, whenever you have two vectors that are not parallel, they're going to span all of R2. And that kind of makes sense in terms of the picture, because you have these two vectors that are pointing in different directions. And so, geometrically, it makes sense that you can take a certain combination of v1 and a certain multiple of v2 and add them and get any vector on the plane. But this wouldn't be true if you had something like how come I can't write? Well, okay, let's say that you had two vectors that were parallel, so they lie on the same line. Well, in that case, you wouldn't be able to get all possible vectors in R2 as a linear combination, because if you have two vectors on the same line, then you could just take any vector that's not on the line, and then that vector will not be a linear combination of the two vectors that are on the line. So I have to stop the video, but we can continue this next time.